I wanted to look at a cool problem from the AtCoder, an AtCoder contest today. So we have, we're given a tree, and we want to count up for every like interval of nodes. Right, the nodes are numbered 1 through n. So like the nodes from 1 to 3 is one interval, the nodes from 2 to 7 is another interval. For all the intervals, we want to add up the number of connected components. If you just take the subtree, like with those vertices and the edges between them. And we want the sum of the number of components across all possible intervals. So in this example, we have a length 3 tree with 3, it's a simple path, 3 in the middle, 1 and 2 on the edges. And the answer is 7. And there's 6 different intervals. And most of them have 1 components, but the one with just the edges, the ends, has 2 components, right? 1 and 2, because they're missing the middle node, which is 3. And note that like we don't have the subset 1 and 3 here, because we only have sort of contiguous intervals. So instead of 2 to the n subsets, that we could possibly form, there's only going to be like n squared, maybe n choose 2 subtrees that we look at. Okay, so that's the problem. So how could we solve it? So sort of the brute force approach would be, well, let's just consider all of those n squared subtrees and run like BFS or something to compute the number of connected components among them. So that would be n cubed, right, because it's n squared trees, and counting the components is going to be linear time. So that's obviously way too slow, n is 200,000. So we need like not an n cubed, but like an n or n log n solution. So another solution, which is n squared, which is sort of an incremental version of the last one. So we could use union find to count the number of components, and then we can go ahead and add edges, right? So like start with L equals 1, and then successively add vertices 2, 3, 4, etc. to get all the subtrees with L equals 1. And the way that you add a vertex is you add all you add that vertex, and then you add all the edges that terminate there to the union find. And so you're only going to go through for each value, for every L, you're only going to go through each edge once as you go through all the values of R. So this whole thing is like linear time for each value of L, so the whole thing is n squared. I'm not fully explaining the solution. There's some details to work out, but they're all fine. But the point is, the solution is way too slow, so who cares? Because n squared is still, what is this, 40 billion operations? And that's too much. So let's talk about the actual solution, which is O of n. The point is that for a given subtree, the number of components is the number of nodes in that subtree minus the number of edges in that subtree. And why is that? There are no cycles in a tree, right? We have a tree, and like sort of the defining feature of a tree, well, it's connected to no cycles, but no cycles. And because there are in a graph with no cycles, every time you add an edge, you decrease the number of components by 1, right? Because you're joining 2 previously unjoined components. If they're already joined, you would have formed a cycle. And so the number of components in a subtree is just the number of nodes minus the number of edges. Right? Each node starts out as its own component. You can think of it this way, and then as you add the edges one by one, they each connect to previously unconnected components. Right? They merge 2 components, decrease the number of components by 1. And so the idea is that we don't need we can sort of break out pieces of this sum. Right? This is like sort of looking at each tree one at a time. But actually what we can do is look at first the sum over the nodes, and then the sum over the edges, and handle them separately. So let's just look at this part, the sum over the nodes. Pretend there were no edges. This part is easier, probably. So just yeah, let's look at it this way that I've written down. So consider all the trees that have L equals 1. So, the node with just 1 has 1 node, the node with 1 and 2 has 2 nodes, the node with 1, 2, 3 has 3 nodes, all the way up to the nodes, 1, 2, 3 up to n has n nodes. So there's, the sum of the numbers from 1 to n is the total number of nodes in all the trees with L equals 1. With L equals 2, you get the same thing, except there's no tree of size n, right? It only goes up to n minus 1. For L equals 3, the same thing, except it's the sum from 1 to n minus 2. So this function, the sum of the numbers from 1 to n, is actually, there's a well-known formula for it. And so why is that the formula, by the way? This is a nice trick. So you pair up, right, the numbers like this. And each of these groups is an n plus 1. Right? And how many of these groups? So this works if n is even, but if n is odd, then you're left over something in the middle. But that leftover something in the middle is exactly n plus 1 over 2. N over 2? No, I guess it should be, yeah, n plus 1 over 2 to make it work. So anyway, this is a good fact to know if you don't know it, and to be able to rederive by this grouping. And so the number of nodes in all of the subtrees, well, it's just Sn for L equals 1, Sn minus 1 for L equal 2, all the way up down to S1 for L equals n. And so because we can compute, we have this formula for Sn, this sum is just linear time, so that's good enough, right? We just want linear time. I'm sure there's a way to simplify this sum because it's so regular, but we don't need to worry about it. So the edge is more complicated. We're actually going to sort of invert the sum, right? Instead of looking at the trees and considering the edges in each tree, we're going to look at the edges and consider which trees each edge is in, because this is easier to do. So it's kind of neat that you can invert the sum that way, right? Because we just want the number of like tree edge pairs. And instead of thinking about it tree first, you can think about it edge first. So let's consider some edge between nodes A and B, where A is less than or equal to B. So that is in the tree, basically just if AB is contained in the interval LR. Right, that is if L is less than or equal to A and B is less than or equal to R. And there's A ways for L to be less than or equal to A. It could be any of the numbers from 1 to A. And there's n minus b plus 1 ways for B to be less than or equal to R, because it can be any of the numbers from B to n. Right, it's a useful thing to know is that the number of numbers, right, the number of numbers from A to B inclusive is B minus A plus 1. This is like the size of the interval, right? So n minus b plus 1 and also a minus 1 plus 1, just a. So how many trees does AB appear in? It appears in this many trees, or intervals, right? Each interval gives us a tree. So that's the whole solution. Let's look at the code. It's actually quite short because this is mostly a conceptual problem. Thinking of the solution is the hard part. Yeah, so we read an n. We're going to count up our answer. We actually don't need to know anything about the edges to compute the nodes part. So this is the node sum, where it's just S1 plus S2 all the way up to Sn. Right? I define the S function which is just this. And now we can do the edges part. So we read in the edge, and we said we needed a less than or equal to b, so it's like the longest part of the code is just to swap a and b, and check that we did it right, and subtract off this, which is how many times that edge decreases the number of components, and that's the whole thing. We just print out the answer. So that was that problem. The hardest problem on the contest, but as you can see, not hard because the coding was hard. The code is actually very short. But just because sort of thinking about the idea and like thinking to break up the sum and thinking to invert sort of the way that you look at the edges is conceptually tricky. So yeah, I thought it was a neat problem. Hopefully you think so too.